In this video, we're going to talk about vertical and horizontal slices. So our goal is to set up some double integrals. Specifically, we're going to set up double integrals over the region R that look like f times dA. And when we write dA, that's either going to represent dx dy or dy dx. So essentially, we're going to look at the difference between these two orders, the difference between doing dx dy versus dy dx, and we'll see how to set up the double integral in both situations. So in this example, we want to set up a double integral over the region R. What we're integrating is f times dA. We're told what the function f is, just the function x. And R is always a region of the xy plane in this context. In this case, it's bounded by the three lines that are described in the question. And in part A, we're going to do the setup using vertical slices, and then we'll do a part B where we go through the exact same problem, but we do it using horizontal slices. So let's start by drawing a picture of this region R. So we're in the xy plane. We're going to have the line y equal 3 on here. We're going to have the line y equal negative x, so maybe we want a few negative x values on here and maybe a few positive x values as well, just to get a sense of what's happening. Okay, so let's start by drawing the line y equal negative x. So it passes through the origin, got a slope of -1, so it's looking like that. Okay, and then y equal x plus 2 has y-intercept of 2. It's got a slope of 1. So it's going through these points here. And then we've got our horizontal line y equal 3. Okay, so I think I will label all these lines. That's going to be important as we get into our calculation. There we go. So what we're doing here is we're trying to get a description of what points x, y lie in this region. The region being this triangle that's enclosed by the three lines. So the first way we're going to approach this is we're going to do vertical slices. So what that means is draw a bunch of vertical lines that are going through your region. So essentially we're just trying to highlight our whole region R, but we're highlighting it by drawing these vertical lines. So one way to capture all the points that lie in this region is to talk about what y values lie in here, and then after that to talk about what x values lie in here. So let's focus in on one of these vertical slices. Let's look over on the left side, for example. So one of these vertical slices goes from the line, has the line y equal 3 forming the top boundary, and it has the line y equal negative x forming the bottom boundary. So we could say that y goes from negative x at the bottom to y equal 3 at the top. But that would only be true until we got to about here. Because at this point, where x equaled -1, see the bottom line changes. In the left part of the diagram, the bottom line is the y equaled -x. And then on the right side of this region R, it's actually the line y equal x plus 2 that's forming the bottom boundary. So we could say, yeah, it's true that y goes from -x at the bottom to 3 at the top, but that would only be true for x values between, let's see, this would be between -3 and -1. So that captures part of our region R, and we've also got another set of values over on the right side of this region. Let's talk about what y is going to range between and then what x is going to range between. Okay, so let's focus in on one of these vertical slices over on the right side of the region R. Let's say, for example, this vertical slice here that we've got in blue. So it is going from y equal x plus 2 at the bottom to y equal 3 at the top. So that's capturing those y values along that slice. And then if we think about what are the x values that all those slices could range between, well, on the right side of the region R, it would be from -1 to +1. Okay, so it helps to have all our x values highlighted there, and it helps to have a clear picture so that we can understand that the x value -1 is the point where those two lines intersect. Now, just as a little aside, if you hadn't drawn a clear picture and you weren't sure where those two lines intersected, if you wanted to get the intersection, you would just say y equal y to find where those 2 points meet. So you'd go -x equal x plus 2, and then you could do a little calculation there and figure out x equal -1 is that intersection. So if you needed more detail, that's how you'd find that x value there. Okay, so we've effectively divided our region R here into two triangles. We've done the left triangle and the right triangle. And generally this method of doing vertical slices just says deal with the y values first. Think about what your y values are ranging between when you do these vertical slices. And then just cast your eye over your entire region and figure out what x values you're capturing. So the x values would be numbers, whereas the y values may be numbers or may depend on x. So you see that in both sides of that region R there. Okay, so now we're going to think about how to finish the problem from there. When we are doing vertical slices, dA is going to be dy dx. We think about our y values first when we're doing a vertical slice, and then we think about x values later. So we use the order dy dx for vertical slices. Okay, let's look back at the question. Just make sure that we understand everything we're supposed to do here. So we are trying to set up a double integral over the region R of f dA, where we're told in the question f is this function x. Okay, so let's do it. So we could say double integral over R of f dA. When you write down your f, you don't necessarily have to write f of xy. You can just write f for short because it's a little cleaner. We can say that's the double integral over R of, well, we're told in the question that our function f is just x, so we sub that in. And because we're doing vertical slices, we write dy dx in that order. Okay, and then the last thing that we need to do is put our values onto the integral, onto the double integral. So the catch with this problem is because we had to divide our region into two subregions, we're actually going to need two different integrals here. So we're going to split this up. One integral for the left side of our region R, and second integral for the right side of our region R. And that's just to make sure that we're capturing all those different x and y values. Okay, so let's put the numbers on here. So whatever differential you have written down first matches up with the inside integral. So if you see dy written down first, then you know you're going to have your y values on the inside integral. Okay, so let's look at the left side of our region. We've got our description right up at the top of the screen. We said the y values were going from -x to 3, and then the x values were going to go from -3 to -1. So that describes the integral, the double integral, of the function x over that left side of the region. And then we still need the double integral of our function x over the right side of our region. Okay, so again, y values will go on the inside integral, x values will go on the outside, and this time we're looking up here to see the description of the right side of our region. Okay, so y values are going to go from x plus 2 to 3, and then our x values are going to go from -1 to 1. So I purposely chose a problem that was a little tricky there in terms of vertical slices. We had to do this trick of splitting our region up into two subregions, and you're going to have to do that if the line that's defining the bottom of your region changes. So if you switch from y equal -x to y equal x plus 2, you'd have to split up into two regions. Similarly, if the curve forming the top of your region changed, then you would have to split up into two regions. So let's try this problem again using horizontal slices, and we'll see that actually goes a lot smoother. So just to avoid having to do too much scrolling, let's write down the important pieces of the question. So we want to set up the double integral over r of f of x, y, dA. We were told in the question that the function that's acting as our f of x, y is just the function x. So that's going to be our integrand. And I'm going to draw a picture of our region so that we've got that in front of us. So we had the horizontal line y equal 3. We had a couple of other lines. So one was the line y equal negative x. And one was the line y equal x plus 2. Okay, and we saw from our previous picture that those lines actually intersect at negative 1, 1. Okay, so we've got some scale on there. We've got most of our lines labeled. Let's label this last line y equal x plus 2, and this time we're going to do horizontal slices. So that means we're trying to capture all the points x, y that lie in our region R. The region R is the region enclosed by these 3 lines, so it's still that same triangle as we were talking about in part A. But now we're going to try to cover all these lines, or all these points in the region by drawing horizontal lines. So just draw these horizontal slices or horizontal lines. If you drew infinitely many of them, then that would be a way of covering all the different points that lie in that region R. Okay, so when we do horizontal slices, we think about the x values first, and then we think about the y values. The reason we do that, if this line is moving horizontally, then we really want to say it's moving from its left endpoint to its right endpoint. So we talk about what's happening in the x direction first, and then we scan over the region as a whole, and we just figure out, oh, what y values are we doing this process for? And because we think about it in that order, when we write down our dA is going to be dx, dy in that order. So essentially the difference between taking dA equal dy dx versus dA equal dx dy, this is the difference between doing vertical slices like we did in part A and horizontal slices like we're doing here. So let's see if we can figure out what our x values are ranging between. We want to focus in on one of these horizontal slices. So let's just pick one. Let's say this one here. The left endpoint is sitting over here, which is on this line y equal negative x. So in order to figure out the x value associated with that line, we actually need to rearrange this equation and just solve it for x. So if we multiplied both sides by -1, we'd have negative y equals x, or in other words, x equals negative y. Okay, so negative y is what's forming the left endpoint there. And we want to do the same thing for the right endpoint. So this right endpoint is lying on the line y equal x plus 2. If we solve for x, x equals y minus 2. So then we can say any horizontal slice in this region here, going from left to right, is going to go from x value negative y to x value y minus 2. No matter whether the horizontal slice is up here or down there, that's going to be true. And then as we just scan over this region as a whole, think about what y values we're doing this process for. Well, the triangle has y values that go from 1 to 3. So I'm just going to highlight the question that we've got up at the top of the screen. So we want to set up the double integral over R of the function f of xy times dA, where our function, our integrand itself, is x. All right, so let's write our answer down here. I'm just going to say double integral is equal to, well, our integrand is x. dA, since we're doing horizontal slices, it's going to be dx dy in that order. X values are going to go on the inside integral, and y values will go on the outside integral. Okay, and then we just need to look up at this box here to figure out what our x and y values were. X was ranging from minus y to y minus 2, and y is ranging from 1 to 3. So that gives us our limits of integration. So depending on the problem, you want to use vertical slices or horizontal slices, depending which one you think would work more efficiently.